Hello, ladies and gentlemen. Today we are going to talk about a couple of right triangles that are special right triangles. And the reason they're special is mainly because we use them all the time. Since we use these particular right triangles so often, it can benefit us to understand or know what their side lengths will be, especially when we have triangles that are equilateral or isosceles and we might need to break them into pieces. These are going to help us out a lot. So what we have is two different kinds of triangles that are defined based on their angles. And the first one is 30, 60, 90 triangles. And what that means is that this triangle has a 30-degree angle, a 60-degree angle, and a 90-degree angle in it. So we've got those three angles. And when we have a triangle with 30 degrees, 60 degrees, and 90 degrees, no matter how big or small the triangle is, its sides will always be in the same ratio to one another. So in a triangle that has a 30, 60, 90 pattern, the side, well, for example, if the side opposite the 30 is 1, then the side that is the hypotenuse will be 2. It's going to be double of what that is. And the side over here, the other leg, is going to be 1 square root of 3. So if this leg is 1 unit long, this will be double of that, and this will be 1 square root of 3. But this is going to work for every 30, 60, 90 triangle. So we can write it as sort of a blank template. So we can make a 30, 60, 90 triangle. And we can say that if this is 30 and this is 60, and we've got our 90-degree angle here, then that means that if this side length is x, if we call that x, whatever it is, it's x, that means that this side length will be 2x. It's going to be double of whatever the shortest leg is. And the other leg is going to be x square roots of 3. So whatever length this bottom leg is that's across from the 30, the leg across from the 60 is going to be that many square roots of 3. So we're going to see that. We're going to get some really easy problems today, and then they're going to ramp up a little bit. So if we have these missing sides, but we know we have a 30, 60, 90 right triangle, right? We know this is 30, 60, 90 because there's a 30 there. There must be if there's a 90 and a 60. The shortest leg, the one across from the 30-degree angle, is 2. That means that the hypotenuse will be double that, will be 4. And then the side over here, the other leg, is going to be 2 square roots of 3. And if you use the Pythagorean theorem and you were to solve these using a squared plus b squared equals c squared, you would see that this is true. This is a true relationship based on the Pythagorean theorem. Right? If this side length is 4, that means that the hypotenuse is double, which is 8, and this side length is 4 square roots of 3. Over here, this side length has a hypotenuse of 6, and then we need to find the short leg, so we're going to take that and make it in half, so that's 3. And the long leg will then be 3 square roots of 3. All right, that's really all there is to it. Sometimes they're tilted, and we don't want to get that confused. So if they are tilted, and we have, for example, 10 is the hypotenuse, we're going to need to make sure that we put the half of that on the side that's across from the 30, right? So here's the side across from the 60. We want to put it on the side across from the 30, so this is 5. And then this side, according to the shortest leg, would be 5 square roots of 3. All right. Sometimes we get the square root of 3 leg already given to us. And if we do that, then we know if this is 4 square roots of 3 across from the 60, then this side is going to be 4, and this side is going to be 8. And then lastly, if this side is 5 root 3, then this side will be 5, and the last side will be 10. Sometimes, and this is where it gets a little bit more tricky, we have a whole number given to us, but that whole number is across from the 60. Now this is the side that is usually x square roots of 3, okay? And in order to find the other two side lengths, we need to figure out how many square roots of 3 this is. We need to rewrite 9 as x square roots of 3, okay? So what I can do is I can make myself an equation, and I can say x square roots of 3 equals 9. So what I'm looking for is I'm looking for the number, just like a 5 that would go here or a 4 that would go here. I'm trying to figure out how many square roots of 3 there are in 9, okay? So to solve this, I would just solve the equation. I would divide both sides by the square root of 3. and I would say x equals 9 over the square root of 3. But like you know, this is not this is not a, what's the word? It's not allowed. We're not allowed to have a square root in the bottom of a fraction, so we have to rationalize this denominator. Remember, we rationalize the denominator by multiplying it by itself, so we'll multiply it by the square root of 3, and we'll multiply the top by the square root of 3 as well to keep it the same. So that means that x is going to equal 9 square roots of 3, 9 square roots of 3 over 3. And since we're going to simplify, then x is going to be equal to 9 over 3, which is 3 root 3, okay? And what that really tells us is if we were writing this as x root 3, we would write 3 root 3 root 3. So the x is 3 root 3. Because this is a whole number, my original starting number, the same way we had a 5 here and a 4 here, is going to be 3 root 3. That means that the side across from my 30 is also 3 root 3. And it means that the side that is my hypotenuse is going to be double the shortest side. So double of 3 root 3 is 6 root 3. Right? We'll do that again over here so you can see it again. So we have a side length that is 6. And we know 6 is a certain number of square roots of 3, right? 5 square roots of 3, 4 square roots of 3. 6 is equal to some square roots of 3. So we'll make the equation 6 equals x root 3. We'll divide both sides by the square root of 3. And that's going to be 6 over the square root of 3 equals x. But of course we need to rationalize that denominator, so we're going to multiply by the square root of 3 over the square root of 3. And we get 6 root 3 over the whole number 3, right? The square root of 3 times itself is 3 equals x. And then finally, let's reduce that because we can reduce 6 over 3, and we get 2 square roots of 3 is x, okay? So this 6 is like 2 square roots of 3 root 3, which means that the base is just 2 square roots of 3, okay? And then we also can double it and get the hypotenuse, and that is 4 square roots of 3. So if this is confusing to you, for the first few when you're doing it in your homework, just focus on copying the process here. Copying the process, copying the pattern, and eventually you'll understand, oh, that's what we're representing when we say the number 6, is how many root 3's we have. We have 2 root 3 of them, all right? The other kind of triangle that we're learning about today is the 45, 45, 90 triangle. All right, this is an isosceles triangle because it's got 2 base angles that are the same, so a 45 degree, a 45 degree, and a 90 degree. And this kind of triangle also has a special pattern, a special ratio of the side lengths that we can memorize, because we're going to see these so often that we probably don't want to use the Pythagorean theorem every time we see them. So if we see a shape like this, a 45, 45, 90 triangle, and it has side length 1 and side length 1, we know they have to be 1 and 1 because they have to be the same since it's isosceles, then the hypotenuse of this triangle will be 1 square root of 2. Right? And if you check yourself with the Pythagorean theorem and do 1 squared plus 1 squared equals c squared, you'll see that that side length should be 1 square root of 2. As a general template, any 45, 45, 90 triangle that you see, so 45, 45, 90 triangle, will have side lengths of x and x on its legs, and then its hypotenuse will be x square roots of 2. Right? There's a pretty easy relationship here. So if we take a look at our examples, we've got a side length of 2 in a 45, 45, 90 triangle, so this is going to be also 2. It's got to be the same. And then this hypotenuse has to be 2 square roots of 2. All right, over here, if we've got a 5, then we have a 5, and we have a 5 square roots of 2. If we start with a 6 square roots of 2, then we know that this side length was 6 and this side length was 6. If we start with a 3 square roots of 2, we know that our side lengths are 3 and 3. But also, the same problem we had before with the whole number being where there should be a square root is going to happen in 45, 45, 90 triangles. So if this side length is 4, we need to figure out what these two are going to be, because we're not used to having a whole number in this spot. So we'll solve it again by doing the same math that we would before. Since this side is the side we normally call x root 2, then we are going to say 4 equals x root 2, and we're going to figure out what that x is going to have to be. So we'll divide both sides by the square root of 2, and that gives us 4 over root 2 equals x, and you're probably seeing what needs to happen here. We need to rationalize this denominator by multiplying by the square root of 2 over the square root of 2, and we get 4 root 2 over the whole number 2 equals x. And then we're going to divide both sides, or divide the top and bottom together here, and we get 2 root 2, which is our x. Right? So if this is 2 root 2 square roots of 2, then this side is 2 root 2, because that's our x, and 2 root 2. All right, same here with 8. We have the whole number 8. We need to figure out what our x is going to be. So we'll say 8 equals x root 2. And divide both sides by the square root of 2. And we get 8 over the square root of 2 equals x. Rationalize that denominator. And we get 8 square roots of 2 over whole number 2. And then we just simplify. We get 4 square roots of 2 is equal to our x. So the x goes in front of the square root of 2 on the hypotenuse side. It would be 4 root 2 root 2. But it's also just the legs. So 4 root 2 is both of the legs of my triangle. The way that this can be really, really helpful is when we're looking at equilateral triangles. So it says triangle ABC is equilateral and side length AB equals 14. It says what are the lengths of BD and AD? So you're looking at this and you say, well, I know that this triangle, which was equilateral, has side lengths 14, 14, and 14, right? And I know that an equilateral triangle has has angles 60 degrees, 60 degrees, and 60 degrees. So if I make an altitude, which is going to come down exactly in the middle, since an equilateral triangle is also isosceles, then I have a 60-degree angle here, and I have a half 60-degree angle here, or a 30-degree angle, and a 90. So I've created a 30, 60, 90 triangle in my equilateral triangle. And now I don't need to use the quadratic formula, or not the quadratic, I don't need to use the Pythagorean theorem at all, because I have a hypotenuse of 14, which means that the short side is half the hypotenuse, so that's 7. That also makes sense because this whole side was 14, and you can divide that by 2 to get 7. And that means that my other leg is going to be my short leg square roots of 3, so 7 square roots of 3 there. So BD, which I was looking for, is 7, and AD, which I was looking for, is 7 square roots of 3. Right? And that's all there is to it. So the first thing that we did in this chapter was we taught you about the Pythagorean theorem and how to use it and why it works. But now for this rest of the chapter, we're basically talking about shortcuts for the Pythagorean theorem. What can we do so we don't always have to use the Pythagorean theorem? And this is one of those things. We can use these shortcut triangles of 30, 60, 90, and 45, 45, 90 to help us out and use the ratios rather than doing the Pythagorean theorem every time. So go ahead and work on the 9.7 worksheet with this. Good luck on everything.